Welcome to section 8.2. Power series methods are an important way to solve a lot of differential equations. And as you can see from this image here, they've been around for a long time. And if you actually look in section 8.8 of your textbook, you'll see a whole chart of differential equations that have to be solved using power series methods, because many of the differential equations we run across every day in life can't be solved using the methods we've learned so far in this course. So on this next page, I've got a flow chart from Calc 2, which you might remember, and this flow chart tells us how to find the radius of convergence for a power series. Now, let's just back up a little bit. What is a power series? It's an infinitely long polynomial. Now, this power series is centered at x naught, but many power series that we work with will look like this, and they'll be centered at 0. The interval of convergence is the set of all x for which the power series converges, and the radius of convergence is half of the width of the interval. And so in order to find the radius of convergence for a power series, you're going to use the ratio test to find rho. And let me just remind you of what rho is in the ratio test. Rho is the limit as n goes to infinity of the absolute value of the n plus 1th term, c sub n plus 1 x to the n plus 1, divided by the nth term, cn x to the n. And the ratio test states that the power series converges absolutely as long as rho is less than 1. And so if rho is equal to 0, r is infinity. If rho is infinity, since infinity is never less than 1, you only get convergence where the power series is centered, and so your radius will be 0. And then this middle case is the in-between case where the radius of convergence is going to depend on x. Okay, but what I want to focus on today is basic arithmetic with power series. Reindexing, adding power series, combining power series. So let's start with addition. If you have two power series and they both start at 0, you can combine them by simply adding their coefficients. So in this example right here, my an is 1/4 cn, and my bn is ncn. And so if I want to add f plus g, since they both start at 0, I can just go ahead and add 0 to infinity, 1/4 cn plus ncn, all times x to the n. And since there's a cn here and a cn here, let's combine those. This is the sum, n equals 0 to infinity of 1/4 plus n parentheses cn x to the n. All right? Typically, they're not quite that easy. Let's look at this next one. Here we've got one that starts at 0 and one that starts at 1. So in that case, in order to add the two power series, you need to start them both at 1, the higher of the two numbers, 0 and 1. So here's how to do that. Take f of x and rewrite it as a power series that starts at 1. So how do you do that? You cull off the 0 term. When n is 0 in f, we get 3c0. All right, and then you're going to get the rest of the terms. That's the sum, n equal 1 to infinity of 3cn x to the n. So now I've written f as a power series that starts at 1. So f plus g is 3c0 plus the sum, n equals 1 to infinity of 3cn x to the n. And now I'll add on g, n equal 1 to infinity of ncn x to the n. And now I can add, so that's equal to 3c0, that guy just hangs out there, and then a single summation sign, 1 to infinity, and 3cn plus ncn is 3 plus n parentheses cn, and then x to the n. Okay, another skill we're going to need is setting power series equal to 0. Now, we won't need this until later in section 8.2 and in section 8.3 when we actually start solving differential equations. The statement that if a polynomial is 0 for all x, all the coefficients have to be 0 generalizes to power series. So if you have a power series that's equal to 0 for all x, then all of the coefficients have to be 0. And so here's an example of how you would apply that. Suppose that this power series is equal to 0. What are the conditions on the CNs? Well, the constant coefficient has to be 0. The coefficient of x has to be 0. The coefficient of x is C1 plus 1. That is 0. So now we know that C1 is -1. And then the coefficients of all the other x's have to be 0. So here are the other coefficients. We have to set that equal to 0. N C sub n plus 1 minus Cn is 0. And that has to be true for, since this summation starts at 2, n equals 2, 3, ... Now, typically when you get an expression like this, you want to solve for the larger Cn. So this implies we're going to solve for Cn plus 1 in terms of Cn. So this implies that Cn plus 1 is Cn over n. And that's called a recurrence relation. And again, we'll deal with those later on. Okay, something that you did learn back in Calc 2 is how to re-index a power series, because we had to do this when we found sums of geometric series. And so I've got my rule here. Whatever you have to do in the formula, you do the opposite down here on the summation sign. So let's look at a couple of examples here. We want to write this power series as a power series in x to the n. That means I need to subtract 1 up here in the exponent on x. So that means down here, I need to add 1. So this is going to be sum n equals 1 to infinity. And then literally everywhere I see an n in that formula, I need to replace it with n minus 1. So this is Cn minus 1. N plus 1 minus 1 is just going to be n, and that's squared, and then x to the n. Okay, now suppose I want to write that as a power series that starts at n equals 3. So similar to what we did on the previous page, we need to cull out the n equal 1 term and the n equal 2 term, and then we'll be able to finish off with n equal 3 to infinity. So the n equal 1 term is C naught x, and when n is 2 in this infinite series up here, I have 4C1 x squared, and then I can just keep going. N equal 3 to infinity, C sub n minus 1, n squared, x to the n. All right, let's practice doing some more of this. In the next 3 examples, we're going to write the expression as a single power series in x to the n, and that usually involves 2 steps. 1, re-indexing your series, and then combining. And in some of your homework problems, I don't know why, but I'm just letting you know ahead of time, you'll find your final answer and just replace n with k, because they'll ask you to use k as your index, not n. All right, so for this first one, I see you've got an n minus 2 in my exponent, so I'm going to need to add 2 everywhere in that formula to get x to the n. So that means on the base of the summation, I subtract 2. So this guy's going to start at 0, go to infinity, and then everywhere I see an n, I replace it with an n plus 2. So get n plus 2, n plus 3 over n plus 2 quantity squared plus 1. The Cn becomes a Cn plus 2 and x to the n. And again, if that was a homework problem, they might ask you to rewrite that. Everywhere you saw an n, you just replace it with a k, but that's literally the only difference. I'm not going to have you do that because I think it's foolish. Okay, step 2 is NA. We don't have to combine any power series because there's only one to begin with. All right, I encourage you for these next 2 to pause the video, do them yourself, and then pick back up. So here we go. For this one, step 1 is NA. I don't have to re-index at all because both of them already start at x to the n. So for step 2, combining, one starts at 2 and the first one starts at 0. So that means I need to take this first one and start it at 2. So I'm going to cull off the first 2 terms. I get C naught plus C1x plus sum n equal 2 to infinity of Cn x to the n. And then I'm going to add on that second infinite series, which is sum n equals 2 to infinity of NCn x to the n. And now I can combine. This is C naught plus C1x, single summation sign, n equal 2 to infinity, and my coefficient will be n plus 1 Cn x to the n. Now, a word about that coefficient there. I've got a Cn, over here is my scrap paper, and I've got an NCN. When the C's are the same, a CN and a CN, you don't want to leave two of them, and that will become clear later on when we solve differential equations. You want to rewrite that as a single CN. So factor out the CN to get n plus 1 CN, and that's what I did over here. Okay, last one, we're going to have to do both things, reindex and combine. So step 1, I need to start this first guy at, let's see, I need to add 1 here, so I'm going to subtract 1 on the base of the index. So that will start at 0, and then n plus 1, c sub n plus 1, x to the n. And then for the second power series, I need to add 2. So I'll subtract 2 on the base, so that one will start at 1 and goes from 1 to infinity, n plus 2, n plus 1, cn plus 2, x to the n. All right, now I want to combine. I need to start them both at 1, the higher of the two numbers 0 and 1. So that means for this guy, I need to cull off the 0 term. So the 0 term is simply going to be c1, and then I can pick up n equal 1 to infinity of n plus 1, c n plus 1, x to the n. And then my second infinite series, I don't do anything to that. N plus 2, n plus 1, cn plus 2, x to the n. Okay, now combine c1 plus single summation that starts at 1. Give yourself a giant set of brackets. The c's are different. I have cn plus 1 and cn plus 2, so I can't combine those, so I'm just going to have to write everything down. I've got n plus 1, cn plus 1, plus n plus 2, n plus 1, cn plus 2, close your brackets, and that is the coefficient of x to the n. And that's it. And that is the end of this part of section 8.2.